Good morning, everyone. Today we are here to present our major project titled Defect Detection in Solar Cells using CNN and Vision Transformer. I am Srigala Maulisheri, bearing the roll number 139, and I am joined by my teammates.
I'm Manisha Rani bearing the roll number 161. I'm Neeli Swati with the roll number of 166.
Our internal guide for this project is Dr. B.V. Ramanamurthy Sir, Professor and Vice Principal, Department of Computer Science. Here is the agenda of our presentation. We will cover abstract, introduction, literature review, existing system, problem statement, objective, model building, implementation, result analysis, limitation, conclusion, future scope, and references. Now my teammate Manisha will continue from here.
Abstract. Our project addresses the problem of surface defects in solar cells like microcracks and finger interruptions, which reduce the efficiency. Traditional CNNs have limitations in capturing long-range dependencies, especially in cluttered or complex backgrounds. Hence, we proposed a hybrid model that integrates efficient net and vision transformers to detect defects from electroluminescence images. The hybrid model leverages local and global feature extractions for better accuracy and robustness. Introduction. India contributes 10.6% to renewable energy through solar power, but defects in polycrystalline panels affect their efficiency. These defects, often caused by thermal stress or mishandling, leads to energy loss. Early and accurate detection is critical. Our model proposes a novel approach using deep learning, combining CNNs and vision transformers to automate and improve defect detection. Literature review. CNN-based encoder-decoder architectures have been used to detect defects, but they often struggle to generalize due to complex patterns and background noise. Literature highlights a gap in long-range dependency modeling. Transformers, with their global attention mechanisms, are capable of bridging this gap. So far in this research, we have noticed that they have used small datasets around 200 to 300 images, which is also considered as one of the limitations. Next will be continued by my friend Mauli.
Existing system. Manual inspection of photovoltaic cells is slow, expensive, and inconsistent. Basic CNNs, although automated, fail in noisy or complex backgrounds. Our project targets this shortcoming by using hybrid of CNN and transformer architecture to enhance defect detection accuracy. Problem statement. Defects such as cracks and discoloration significantly reduce photovoltaic cells efficiency. Manual inspection is not scalable. We aim to automate defect detection using hybrid CNN transformer model. The CNN captures fine details while transformers handle the global spatial dependencies. Objectives. Our objectives include develop a hybrid model using efficient net and vision transformer, improve defect detection and classification accuracy, reduce false negative and positives, lower conceptual cost without sacrificing performance, eliminating manual inspection by automating the analysis of electroluminescent images. Dataset and feature extraction. For our project, we have dataset which is constructed in a way where it contains a folder of 1000 electroluminescent images and a CSV file which contains respective paths and the image with corresponding labels. In order to avoid overfitting, we have balanced the dataset into 500 defective, 500 non-defective images, including features such as texture irregularity, brightness, variance, and shape discoloration. Images and labels are read from CSV using pandas. Paths are constructed using OS and Python imaging library is used to resize image to 224 cross 224 and convert them to RGB. NumPy arrays are used to construct data for model input. Proposed model. The proposed model integrates the efficient net and vision transformer to enhance the accuracy and defect detection in photovoltaic cells using electroluminescent images. Efficient net is used for local feature extraction, capturing fine details of defects such as cracks and contamination. Vision Transformer analyze global spatial relationships, ensuring better defect classification across different scales. The hybrid approach combines CNN strength in localized feature extraction with Vision Transformer ability to model long-range dependencies. This fusion is designed to improve accuracy and robustness in defect detection, minimizing the misclassification of errors. The flow of architectural diagram. The process starts by breaking the image into small pieces which are called as patches and preparing them so that the model can understand them. Efficient net improves the patches by adding important details from both shallow and deep layers. Then the transformer helps the model focus on different parts of the image to learn relationships between them. Next, patch merging is done, combining the patches to make them fewer but richer in information. These combined patches are processed by CNN, which extracts the important features like shape or edges. The processed data goes through the neck to organize it. And finally, the classifier predicts what objects are in the image, where they are located. All these steps are connected in a flow, passing the information from one to the next to improve the prediction. The implementation is explained by Swati.
Implementation. In this phase, we are importing the core libraries needed for data handling, image processing, and model creation. We have used TensorFlow and Keras for our deep learning, NumPy and Pandas for data manipulation, and PIL for image processing. Here in this step, we are loading image paths as well as the labels in order to clean missing values and unwanted rows and constructing the full paths of the images. Now we are resizing the images of dataset into 224 by 224 pixels while converting them into RGB format so that it can be taken as input for efficient net. And also we have split the dataset into two parts, that is 80% for training and 20% for testing. Now we have applied the one-hot encoding wherein which we are converting categorical labels into numerical format that deep learning models can understand. As well as we are also performing data augmentation with the use of library called image data generator, wherein which we are applying data rotation, wherein which we are doing rotation, zooming, flipping, width and height shifts to enhance the training process. Here comes the hybrid model design, wherein which it is divided into three steps. Firstly, efficient, wherein which the image is been imported and it has been processed through multiple layers of CNN as it is trained on ImageNet, so it can capture the visual features effectively, as well as the feature map is then sent to global pooling layer wherein which the feature map is being comprised, which gives the summary of spatial features. Now comes the transformer module, where firstly we perform patch extraction, where the image is being split into non-overlapping patches, and then patch embedding is being performed, wherein which we'll gain the meaningful insights from each of the patch, and also positional embedding is done, wherein which we'll get to know where the each patch is located in original image. Now in transformer block, self-attention mechanism is being performed in order to find the relationship between each of the patches in the image, and then the output is being sent to multi-layer perceptron. Then we are sending it to final layer. And also normalization and normalization and dropouts are being done in order to reduce the overfitting in transformer module. Then the outputs of CNN as well as transformer module will be concatenated together, and it is sent to dense layer with a softmax activation function. Now comes the training phase, wherein which the model is being trained for 20 epochs using data augmentation with a batch size of 32 at each time. By using early stopping, if the model doesn't increase its validation accuracy up to 5 epochs. And also we have used evaluating metrics such as accuracy, precision, etc. and also used visualization techniques such as confusion matrix for representing misclassified and correctly classified samples from the dataset. Now we have saved our model so that we can use it for further use. Now in this step we can upload a new test image so that we can get to know whether the image of solar cell is defective or non-defective. This is the confusion matrix of our hybrid model, wherein which 86 non-defective samples and 93 defective samples are classified correctly, while 7 non-defective and 14 defective ones are misclassified. Now let me share my screen in order to show the live execution. This is the GUI of our project, which is built using TK-Inter module. Here is an option of open image in order to upload the new sample data. As we can see, it has been detected as solar cell is non-defective. Also, there are no cracks or hotspots on the solar cell. Now let me upload the other solar cell. Now it is classified as a defective solar cell, as we can see cracks on the solar cell. Now comes the limitations of our model, that is, it is highly dependent upon the large data set. The model performance heavily relies on diverse and quality of the training data, and lacks of sufficient defect samples may affect its generalization. And also, as we are using hybrid model, it increases the complexity of the model, so it needs high performance hardware and requires GPUs and TPUs for efficient training. And also sensitivity to environmental variation, the model performance may degrade. Now comes the conclusion. Our project successfully implements hybrid model by combining the strengths of CNN and Vision Transformer, where it captures local and global features, and also system achieves accuracy ranging in between 88 to 90%, and also provides a user-friendly GUI by using TK-Inter module, where we can upload our image and the prediction process is being done. The approach enhances the reliability of defect detection of solar cells. The future scope. We can integrate the system with IoT-based monitoring system so that it can monitor health of solar cells and gives the alerts instantly. And also we can use multi-model data that such as thermal imaging and electrical performance metrics from other resources. Also, collecting data from different varying environmental conditions would be a great approach. Also, embedding our model in drones or robotics also makes our model better. Now we would like to thank our guide, Dr. B.V. Ramanamurthy sir, for his constant support. We also thank the department and faculty for providing resources and guidance throughout our project.